Hello everyone. We are now going to do our sixth lab. It's entitled RC Circuit Lab. But first of all, I'd like to apologize for the sound last time. I had my fan on, and because of that, the sound wasn't great. But today, I have decided to turn off my fan, so we will see some improvement. Now, the first thing I would like to do is, so if we go back to the circuit, so this is what your circuit should look like. Okay, so the first thing I would like to do is to click on the resistor. So the resistor is here, and find the resistance of this resistor. Okay, so the convention in this simulation is that our resistors will be 4-band color coded. Okay, so we'll use 4-band color code resistors. Now, what does that mean? Well, we will have to read the bands from the left to the right. The first band will be the one on the left. The second band will be the one that comes after it to its right, and the third band will be the one that comes to the right of the second one. Okay. There's also a fourth band, but that fourth band corresponds to the tolerance of the resistor, and we will not worry about that in this lab. Now, let's determine the resistance of this resistor. Well, according to the charts that are provided to you in the instruction file, in the link in the instruction file, when the first band is yellow, the first digit of the resistance is a 4. When the second band is red, the second digit is 2. When the third band is orange, the third band for a 4-band color code corresponds to the decimal multiplier. And so when the third band is orange, the decimal multiplier is 1000. Okay? Therefore, the resistance will be 42 times 1000. 42 times 1000, that's 42,000 ohms. The resistance of this resistor will be 42,000 ohms, or 42 kilo ohms. But because you will have a different combination of colors, you will of course have a different resistance for your resistor. Okay? Now let's go back to the circuit and find the capacitance of our capacitor. Go to the capacitor, 2 plates, click on it, and read that the resistance is 1000 microfarads. Okay? 1000 microfarads. Okay? So go back to the circuit. Now, the next thing I would like to do is determine the time constant, tau. The time constant is the resistance times the capacitance, so RC. So tau equals RC. When I multiply the two, I'm going to convert them to SI units, so that in the end I will get the time in seconds, the time constant in seconds. So 42 kilo ohms times 1000 microfarads, so resistance times the capacitance, in SI units is 42 times 10 to the third ohms times 10 to the third times 10 to the negative 6 farads. Okay, micro means 10 to the negative 6. When I multiply all of this together, I find 42 ohm farads, or 42 seconds. So our time constant is 42 seconds. Now, let's find the voltage across our resistor. In order to do that, we first have to click on charge cap. Okay, just did that. Click on the voltmeter, and I read that the voltage across the resistor is 9 volts. Now let's find the current. The current in our circuit is, click on the ammeter, the current is 213.3 microamperes. 213.3 microamperes. Let's go back to the circuit. And then set up the table. Okay? That will record the data on time, voltage, and current. Okay? In order to do that, I will start the timer by clicking on resume, and I will stop it every 10 seconds. Okay, just clicked on resume, and I will click on pause after 10 seconds. You can decide to have 20-second intervals if you want to, but I'm going to do 10 seconds. So, click on the voltmeter, and I read that the voltage is 7 volts. The ammeter, the voltage is 166.3. Okay, good. Click on resume, and I will stop at 20. Okay. The voltage is 5.5. And the current is 131.2. Okay. Where are we going to stop? According to the instructions, we have to stop when we reach approximately 25% of the original voltage. You remember that the original voltage was 9 volts, so 25% of 9 volts is a fourth of 9 volts, and that's 2.25 volts. So we will stop when the voltage goes a little bit below 2.25 volts. Okay. We resume the timer and stop at 30 seconds. Okay. Voltage is 4.4 volts. Current is 103.5 microamperes. Okay, let's keep going and stop at 40 seconds. The voltage is 3.4 volts. And the current is 81.5. Okay, let's keep going. Okay, the voltage is 2.7 at 50 seconds, and the current is 64.3. We keep going. Okay, at 60 seconds, the voltage is 2.1 and the current is 50.6 microamperes. Okay, so we are below 2.25 volts. 2.25 is 25% of 9 volts, so we can stop here. Okay. Now, it would be great to check whether our results are correct or not. Okay. Did we make a mistake in the calculations or in our measurements? Well, let's find that out. Well, we know that the time constant tells us the time it takes for the voltage across the resistor to drop to 36.8% of its original value, which was 9 volts in our case. Okay, so what's 36.8% of 9 volts? Well, that's 0.368 0.368 or 0.37 if you want to, times 9. I'm finding 3.31 volts. Okay, so 36.8% of 9 volts is 3.31 volts. So at time equal to the time constant, so 42 seconds, remember that's the value we found for the time constant earlier, we should have a voltage across our resistor of 3.31 volts. So if I consult my table, I find that at 40 seconds I have 3.4 volts. Okay, and you see by looking at the numbers in the table, the voltage goes down as time passes. So at time corresponding to the time constant, time 42 seconds, the voltage should be, because 42 seconds is a little bit above 40 seconds, the voltage should be a little bit lower than 3.4 volts. And we've calculated that 36.8% of 9 volts is 3.31, should be 3.31. So that's not far. 3.4 volts is not far from 3.31. So that means that we are on the right track. Okay. Now, you are also asked to graph the voltage against time and the current against time. I'm going to show you how to do that using an Excel file in the next video. Thank you.